Welcome to Introduction to Building Codes, Bangladesh National Building Code 2020, referred to as BNBC 2020, Part 8 Building Services, Chapter 7 Rainwater Management. The description of this course is designed to familiarize and assist code officials in locating, describing, and applying the applicable code requirements for rainwater management systems in buildings. The overview of this course helps us understand why internationally code officials recognize the need for sustainability and a code that addresses the water conservation through the design and installation of rainwater management systems. This presentation will cover key topics of the following areas. We will discuss the purpose of this code. We will discuss scope and terminology, along with general provisions and planning for rainwater management systems, including rainwater management system design. We will carry through several examples to help the participants understand proper design and inspection of rainwater management systems. Our seminar goal is as follows. The goal of this training is for you to learn and apply key code requirements contained in Chapter 7 titled Rainwater Management to enhance your performance while inspecting these systems. This training will also provide participants with specific code requirements with examples related to design, installation, and inspection of rainwater management systems in buildings to further enhance your knowledge. The objectives. Upon completion, participants will be better able to locate general topics in Chapter 7 regarding rainwater management, locate applicable codes and standards for specific situations, apply code requirements to real-world situations, explain the intent behind a given code requirement, and use good judgment to identify certain systems and related components as compliant or non-compliant. Chapter 7, Section 7.1, titled Purpose. The purpose of this chapter is to set forth provisions for planning, design, and installation of rainwater management systems in buildings. A rainwater management code cannot be effective without adequate provisions for its administration and enforcement. The Rainwater Management Code intends to establish a minimum acceptable level of safety regarding the use of rainwater in a variety of applications, including but not limited to drinking, cooking, washing, and bathing. The code official has the responsibility for establishing that the homes in which the citizens of the community reside and the buildings in which they work are designed and constructed to utilize rainwater management systems reasonably free of the hazards inherent with such systems. Section 7.1 Purpose continued. The official charged with the administration and enforcement of rainwater management system regulations has a great responsibility, and with this responsibility drives authority. Let's take a closer look at specific sections related to scope and terminology requirements for rainwater management systems in buildings. Section 7.2, Scope. 7.2.1. This chapter specifies the general requirements for rainwater harvesting for different categories of buildings according to their occupancy classification, together with all ancillary works of groundwater recharging such as perforated piping, pits, and inspection chambers. This first part of this section covers rainwater harvesting or collection from building elements such as walls, roofs, balconies, and similar components of buildings, and subsequent use of the captured rainwater based on the building's function. Rather, it may be an apartment, a school, an office building, or some other function of a building. The code is applicable from the initial design of rainwater management system through installation and construction and into the maintenance of the system. Section 7.2.2. This chapter also covers the design, installation, and maintenance of elements for rainwater drainage systems around the building and to public storm sewers or to nearby suitable surface water systems. The second part of this section covers systems that convey water, that is, rainwater, from buildings to stormwater outlets. It should be noted that stormwater drainage on the ground, such as parking lots, runoff areas, is outside of the scope of this code. Again, so any stormwater drainage on the ground is definitely outside the scope of this code. This section makes it very clear to the limitations of rainwater management systems covered in this chapter. Section 7.3, Terminology. This section provides an alphabetical list of all terms used and applicable to this chapter of the code. In case of any conflict or contradiction between a definition given in this section and that in any other chapter or part of the code, the meaning specified in this chapter shall govern for interpretation of the provisions of this chapter. A code provision could be misinterpreted if the definition of a term as used in the context of the code is not understood. The following slides will provide key definitions that will assist the code user to properly understand certain terminology related to this chapter. Codes, by their very nature, are technical documents. As such, literally every word, term, and punctuation mark can add to or change the meaning of the intended result. This chapter contains several terms that are important to understand the provisions of this code. Definitions are found both in this chapter and throughout the code. Let's look at some key terminology relating to rainwater management systems. Branch is defined as any part of the piping system other than a main, riser, or stack. Drainage system gives us a specific definition. A drainage system includes all of the piping within public or private premises, which conveys sewage, rainwater, or other liquid waste to a legal point of disposal, but does not include the mains of a public sewer system or a private or public sewage treatment or disposal plant. We have a drawing indicating a drainage system and components. The example of drainage system conveying waste from fixtures to the sanitary building drain, then to the sanitary building sewer. Looking at the drawing, we can observe the sanitary building drain within the building below the second floor level. This is the location that conveys the discharge from all of the fixtures connected above. The piping is sloped downward and conveyed to the outside of the building into the sanitary building sewer. As can be seen as well, we have what's called a building subdrain, in which condition the lavatory, the shower, and the water closet below the slab floor level in the lower level of the building conveys all of the discharge to a gas-tight sump. In this case, the discharge is pumped from this sump through a check valve and a full open valve and discharges it into the sanitary building drain, and then by gravity it flows through the building drain and conveys that discharge into the building sewer. The term building drain gives us an identification of what this particular segment of the building drainage system is. It is defined as the building drain is that part of the lowest piping or open channel of a drainage system, which receives the discharges from soil, waste, and other drainage systems inside the walls of the building and conveys the same to the building sewer, beginning at 0.9 meters outside of the building wall. As you can see, the graphic at the bottom of the slide indicates the building drain as being the lowest piping indicated within the building. It then extends 0.9 meters from the outside of the building wall. That is where the building drain ends. From that point, the next part of the piping system is titled building sewer. The building sewer connects from the end of the building drain and ties into the sewer main in the case of this graphic. By definition, the building sewer is as follows. The building sewer is that part of the horizontal piping of a drainage system which extends from the end of the building drain and which receives the discharge of the building drain and conveys it to a public sewer, a private sewer, individual sewage disposal system, or other point of disposal. This is also known as sewer. Lastly, the term public sewer. This is a common sewer directly controlled by public authority, also known as main sewer. As you can see, definitions are very specific, and in this case, it lays out the demarcation of where one system begins, one system ends, and the connection between the two distinct systems. Building storm drain. A building storm drain is a building drain used for conveying rainwater, surface water, groundwater, subsurface water, condensate cooling water, or other similar discharge to a building storm sewer or a combined sewer, extending to a part not less than 0.9 meters outside the building wall, also known as a storm drain. Several terms related to rainwater management are as follows. Leader, a vertical drainage pipe that carries rainwater from roof or gutter drain to building storm drain or building drain or private disposal system. Subsoil drain is a subsoil drain which receives only subsurface or seepage water and conveys it to a place of disposal. Trap. A trap is a fitting or device so designed and constructed as to provide, when properly vented, a liquid seal which will prevent the back passage of air without materially affecting the flow of sewage or wastewater through it. The trap seal is the maximum vertical depth of liquid that a trap will retain, measured between the crown weir and the top of the dip of the trap. Indicated below is a graphic indicating a trap piped to a vent connection. As can be seen on the rightmost part, we have an inlet going into a trap. The fluid goes up above the dip of the trap and spills over the weir or the crown weir into the horizontal pipe, and the direction of flow is indicated by the arrow into a sanitary T and downward into the drainage system. The top of the sanitary T is where the vent connection will take place and be piped to an approved venting section of the drainage system. To the right, we have a description of what a trap is, along with the terminology for that particular trap. As indicated in the top, we have the inlet into the trap. The dip is defined as the topmost part of the curve indicated in the trap. The seal is measured from the top of the dip to the very topmost part of the weir. This is at which the fluid spills over into the outlet. That vertical distance measured from the top of the dip to the weir is known as seal. This is where we have the liquid seal to prevent any type of gases to migrate back into the building. An example of storm and subsoil drainage systems. As indicated in the dashed line, we start at the top of the building. We have a roof drain that collects rainwater. Rainwater is captured by sloping the roof downward towards the roof drain inlet. As the water is conveyed through the roof drain, it is channeled downward into what we call a conductor inside of the building. That water runs vertically downward into the building storm drain. The building storm drain extends 0.9 meter outside of the building. Once it connects to the next pipe, titled building storm sewer, it is conveyed accordingly off-site or to a rainwater catchment system. Below the building storm drain is a subsoil drainage system. The subsoil drainage system is piped into a sump, which is a depression below the slab designed to collect subsoil drainage. When the elevation of water rises in the sump, there is a sump pump that is equipped with a float switch that automatically turns the sump pump on and allows the water to be pumped up and into the building storm drain to allow for gravity flow out of the building. This is an example of storm and subsoil drainage system piping. Additionally, on the top of the building, to the right of the building on the exterior wall, there is a leader or downspout which conveys stormwater that is channeled to the edge of the building and downward into the leader that ties directly into the building storm sewer system. Horizontal pipe is defined as any pipe or fitting which is installed in a horizontal position or which makes an angle of less than 45 degrees with the horizontal. When we look at the drawing below, we can see a pipe designed as a horizontal branch or horizontal branch drain. Looking at this particular pipe, we can verify that this is properly defined as a horizontal pipe according to the definition. A vertical pipe is any pipe which is installed in a vertical position or which makes an angle of not more than 45 degrees with the vertical. Again, looking at our drawing, we have a pipe called a water riser. We can see the water riser is a vertical pipe as well as the stack indicated on the left-hand side of the drawing. The stack and the stack vent, which rises above the stack, are vertical pipes and they meet the definition accordingly. Section 7.4, titled Rainwater Harvesting Requirements, gives us section 7.4.1 that requires every building proposed for constructing on lots having an extent of 300 square meters or above shall have facilities for conserving and harvesting rainwater. This section provides the threshold at which conserving and harvesting rainwater is required for a building. However, this section does not prohibit conserving or harvesting rainwater for smaller buildings. Section 7.5, Rainwater Harvesting Plans. We start off in section 7.5.1, Requirement of Permit. Rainwater harvesting and drainage systems shall not be installed until a permit for such work has been issued by the building authority for existing or a new building or for any other premises. Rainwater management systems, especially systems utilized for drinking water, could have severe consequences for building inhabitants if not designed, constructed, or maintained in accordance with the provisions of this code. A permit from the building authority is a crucial step in the process. The permit requirement will also give the applicant a requirement to submit construction documents for review and approval. Additionally, we're really concerned about the materials, the connection methods, and where we are getting the rainwater from and the treatment of rainwater before it is allowed to be reused for some purpose. Section 7.5.2, Application for Permit. An application for a permit for rainwater harvesting and drainage work shall be made on a prescriptive form. The reference here is Appendix Q. The prescribed form must be submitted by the licensed plumber and the owner, or by his appointed person or agent, to install or a self-contained or workable part of such work. The application shall accompany building rainwater harvesting and drainage plans and adequate description of the proposed rainwater harvesting and drainage installation in a drawing with the following details. The drawing must be drawn to a scale not less than 1:100. Item A, plan of the building and site layout. As can be seen in the site plan, to the right, we have a layout indicating stormwater piping, areas where we collect the stormwater. Item B indicates rainwater harvesting. The applicant would have to show the type of rainwater harvesting system that is being designed with details. Item C, ground recharging system. Item D, storm drainage system. Item E, the catchment areas. Item F, materials, sizes, and gradients of all proposed piping. G, the position of manhole, rainwater pipe, gutters, rainwater inlets, etc., in the premises and their connection with storm sewer system or surface waters. The following colors may be used to indicate sewers, rainwater pipes, and existing works, as follows. Proposed storm sewers and disposal pipes may be allowed the color violet to indicate these systems. Existing network, colored black. And then finally H, the slope of catchments must be indicated on the drawings. This gives a pretty detailed list of what is required along with the permit. This will give a clear distinction, routing, type of materials, equipment, and any other appliances that may be part of the rainwater harvesting and drainage system for review and approval by the authority. Permits and approvals are in section 7.5.5. The building official shall examine or cause to be examined all applications for permits and amendments thereto within 45 days. If the application does not conform to the requirements of all pertinent laws, such application shall be rejected in writing, stating the reasons therefor. If the proposed work satisfies all code requirements, the authority shall issue a non-transferable permit. This section requires the building official to act with reasonable speed on a permit application. The building official must refuse to issue a permit when the application and accompanying documents do not conform to the code. In order to ensure effective communication and due process of law, the reasons for denial of an application for a permit are required to be in writing. Once the building official determines that the work described conforms to the code and other applicable laws, the permit must be issued. Section 7.6, Licensing of Plumber. Specific requirements are given in this code for qualified people to install harvesting and drainage work. Section 7.6.1 indicates no individual, partnership, corporation, or firm shall engage in the business of installation, repair, or alteration of rainwater harvesting and drainage work without obtaining a license from the authority. This section mandates that any plumbing work must only be executed by a qualified plumber. Licensure of qualified plumbers is a requirement in this section for installation, repair, or alteration of rainwater harvesting and drainage systems. Plumbing work shall be executed only by a licensed plumber under the control of the authority and shall be responsible to carry out all lawful directions given by the authority. This reaffirms that qualified individuals must install these systems in accordance with this code, and the license is given to the plumber after certain qualifications. Those qualifications will be indicated in the next slide. Section 7.6.2, titled Examination and Certification. The authority shall establish a plumber's examination board. The board will determine the requirements for the qualification and procedures for examination of applicants for license. The authority will issue license to such applicants who meet the qualifications therefor and successfully pass the examination conducted by the board. In order to qualify as a licensed plumber, the authority establishes an examination board. The qualified individuals must be qualified by meeting academic, vocational, and experience requirements as set forth by the examination board. Additionally, they must complete and pass an examination. This process ensures the safety of people by allowing only qualified people to install, repair, and alter rainwater harvesting and drainage systems. However, given in section 7.6.3, the license of a licensed plumber may be nullified by the authority if it is proved that a plumbing work has been completed and certified by the licensed plumber violating the provisions of this code deliberately, setting aside the approvals given in the permit or without receiving the permit from the authority. This last section gives the penalties of licensed plumbers doing work without permits and deliberately setting aside approvals given in the permit as well. Section 7.7, titled Rainwater Harvesting. In the general section of 7.7.1, rainwater can be conserved and used in all useful purposes relating to the use of water. The amount of rainwater to be conserved depends upon the use, rainfall intensity at the locality, and the available catchments from where rainwater shall be collected. Rainwater can also be used for artificial groundwater recharging. Two major aspects of rainwater harvesting are as follows: rooftop rainwater harvesting and artificial groundwater recharge. The function of rooftop rainwater harvesting is to collect it for later use for a multitude of uses, including but not limited to showers, lavatories, toilets, laundry, fountains, drinking water, cleaning, and fire protection systems. The function of artificial groundwater recharge is to supply water to underground aquifers, which can also be utilized for the previously mentioned uses. Section 7.8, titled Rooftop Rainwater Harvesting. Precautions in rainwater harvesting is given in section 7.8.1. The following precaution shall be taken for rainwater harvesting. This is the first part of the system where we harvest the rainwater. Item A, No sewage or wastewater should be admitted into the system. Item B, any wastewater from areas likely to have oil, grease, or other pollutants shall not be connected to the system. Item C, each rainwater seepage well shall have an inlet chamber with silt trap to prevent any silt from finding its way into the subsoil water. Item D, the well should be terminated at least 5 meters above the natural static subsoil water at its highest level so that the incoming flow passes through the natural ground condition and to prevent contamination hazards. Item E, no recharge structure or well shall be used for drawing water for any purpose. This list indicates certain contamination like sewage and wastewater and oil and grease or other pollutants are prohibited from entering this particular part of the system that we call the rainwater harvesting part of the system, as well as wells terminating at least 5 meters above the static subsoil water, and specifically no recharge structure or well can be used for drawing water for any purpose. This lays out a specific list of precautions that the designer must know and properly design around to bring in clean rainwater for harvesting. Each rainwater seepage well shall have an inlet chamber with a silt trap to prevent any silt from finding its way into the subsoil water. The well should be terminated at least 5 meters above the natural static subsoil water at its highest level, so that the incoming flow passes through the natural ground condition and prevents contamination hazards. Again, no recharge structure or well shall be used for drawing water in any purpose. Here's an example of a groundwater recharge structure. The structure, masonry, brick, or block, or concrete, is used to enclose various sizes of sand, gravel, and other aggregate to filter silt from the rainwater as it passes through. The rainwater is collected from a building via the gutter and downspout system and enters the structure at the inlet. It then passes through the filter where silt is trapped. The bottom of the filter should be at least 5 meters above the highest groundwater table, so an additional level of filtration is achieved. Note that groundwater shall not be drawn from the recharge structure for any purpose. Qualifying rainwater for harvesting is indicated in section 7.8.2. Rainwater shall be treated adopting following methods mentioned according to the purpose of use. A, for using rainwater in drinking, cooking, washing, utensils, bathing, and ablution, it shall be disinfected along with filtration. Item B, for clothes washing, floor washing, fountain, waterfall cascade, etc., rainwater shall be filtered. As you can see, B differs from A in that we will not be drinking the water as indicated in item B. Therefore, disinfection is not required. Only filtration is required. Item C, for using in sprinkler, firefighting, air conditioning, etc., sedimentation of suspended particles will be required to be filtered. Item D, for toilet flushing, gardening, cleaning artificial ground, parking lots, etc., screening floating materials are needed. This gives us a well-rounded itemized list of qualifying rainwater for different types of applications and whether disinfection, filtration, and removal of sedimentation is required. Catchments area for collecting rainwater. As indicated in section 7.8.3, rainwater can be collected from the following built-up areas for harvesting. We can collect rainwater from rooftop surfaces, external walls and other vertical surfaces, balconies, sunshades, metal surface of playgrounds, open yards, etc. The intended areas of buildings utilized for rainwater harvesting are washed with rainwater on a regular basis and are cleaner. There is less sediment and particulates on these surfaces and have a lower chance of containing other harmful contaminants. Determining the catchment area. Specifically, we need to look at section 7.8.4. For flat surface, the catchment area is its plan area plus 50% of the adjoining vertical wall, contributing rainwater accumulation on the concerned catchment. The reference is see Appendix U. For sloping roof, catchment is considered to be the actual inclined roof area. The catchment area is the surface that will be used to calculate the amount of rainwater to be harvested for reuse in a given rainfall. The graphic indicated on the right-hand side of the slide, this figure is 8.U.1 from Appendix U as referenced in the previous slide and shows a building having flat roofs at different levels. We'll walk through how to determine the catchment areas for flat surfaces on a building. In level T3, the area bounded by A, B, C, and D is the catchment area, contributing to the rainwater downpipe RDP3. As we look at the graphic on the right, the topmost portion, we can see the corners A, B, C, D. This entire area is actually sloped from AB to CD, as the slope of the roof allows rainwater to channel downward and into the inlet of the downpipe indicated RDP3. In level T2, horizontal area EFGH, and 50% of the vertical wall surface area, AFGM, is also indicated as the catchment area. Projecting above is the catchment area of the rainwater downpipe, RDP2. As can be seen, our roof elevation T2 carries all of that water entering the downpipe indicated as RDP2 down to the lowest roof level indicated T1. For the rainwater downpipe, RDP1, the catchment area will be the horizontal area, IJKL as indicated, and 50% of the adjacent contributory walls as GHIJ and DMJK, plus the rainwater from pipe RDP2. So as can be seen here, the downpipe RDP1 carries quite a lot of water and must be designed to convey that amount of water from the wall surfaces and the roof above, as well as the roof surface indicated T1 from the boundaries of IJLK. Storing rainwater is the second component. First is the harvesting. We look at the roof, we look at the wall surfaces. Now, section 7.8.5 introduces where rainwater will be used for domestic purposes. Rainwater from roof or terrace may be led straight from conductor or leader to one or more storage tanks. Storage tanks shall be provided with ventilating covers. An arrangement shall be made in the rainwater leader to divert the first flush washings from the roof or terrace catchments, as they will contain more undesirable materials. The open end of all pipes shall be covered with mosquito or insect-proof wire nets. If left unprotected, storage tanks could become a habitat for mosquitoes and other insects, which can carry disease that are less than desirable in water used for domestic purposes. And also indicated was to divert the first flush washings of rainwater. This will allow a lot of sediment and debris, plant material, to be purged and not enter the storage container based on the first flushing. Flushing out first rainwater is indicated in section 7.8.6. Before storing initial rainwater, just after starting raining, shall be drained out for a period as mentioned below. The location and time are given in this specific section. Locations such as Dhaka, the metropolitan area, 20-minute is needed for initial flushing before storing rainwater. The location Chittagong, 15 minutes. Other urban areas as well, 15 minutes. Pictured is a common arrangement of a first flush diverter off to the lower right-hand side of the slide. These are used to divert a small quantity of initial volume collected from each rain event. Most of the rainwater that would contain contaminants deposited since the previous rain is prevented from entering the tank. The required volume is subject to the criteria contained in this section. The devices are typically automatic draining and must be accessible for maintenance. As can be seen in the graphic, water flow from the roof is directed into the pipe and dropped down. Thus, the first flush is going down the pipe and being trapped and discharged in the bottom of the automatic drain. As the water comes up the riser, the ball seals the chamber off after a predetermined amount of volume of rain has discharged. The ball seals on the top, so clean rainwater flowing from the surface enters the tank across the pipe accordingly. An example of a rainwater collection system is given in the graphic on this slide. The example here of a rooftop rainwater harvesting system, starting with rainwater falling onto the roof or collection surface. From there, it will flow to the gutters, which will carry it to the main collection pipe. A debris excluder is useful at the transition from the gutter to the collection pipe and is used to filter out larger debris like sticks, leaves, and larger sediment. After entering the collection pipe, the initial flow that may have flush contaminants from the roof will be wasted through the first flush diverter. From there, the rainwater will enter a storage tank. The storage tank must be vented to allow the tank to remain at atmospheric pressure. As rainwater is added and removed, last, the overflow on the tank allows excessive rainwater to exit the tank in a controlled way. As indicated, the overflow goes into a catchment gutter and down to a downpipe and may enter a storm drainage system or the soil below. Section 7.8.8 Rainwater Treatment. For potable systems, a galvanized roof or metal roof with epoxy or latex paint is recommended. Composite or asphalt shingles are not advisable. Asphalt shingles are not advisable because they break down over time and release particles that contain hydrocarbons which are not desirable in harvested rainwater. The texture of asphalt shingles is also rough and would allow for the collection of contaminants, unlike metal roofs, which tend to be much smoother. We must be concerned with proper disinfection. Chlorination is indicated in section 7.8.8.1. Chlorine must be present in a concentration of 1 part per million to achieve disinfection. Liquid chlorine in the form of laundry bleach usually has 6% available sodium hypochlorite. For disinfection purposes, 2 fluid ounces, quarter cup, must be added per 1,000 gallons of rainwater. Bleach products, however, not labeled, cannot be used in water treatment. A purer form of chlorine, which comes in solid form, is calcium hypochlorite, usually with 75% available chlorine. At that strength, 0.8 ounces by weight in 1,000 gallons of water would result in a level of 1 part per million. Chlorine is a commonly used and widely available disinfectant. It's important to know that the concentration of chlorine be added to the rainwater. Too little chlorine will not effectively disinfect, and too much chlorine can be hazardous to humans, animals, and plant life. So one must be careful when disinfecting the system and use the ratios accordingly in a safe manner for disinfection. Chlorine contact times are shown in Table 8.7.1. To filter out Giardia and Cryptosporidium cysts, an absolute 1 micron filter must and shall be used. Table 8.7.1 indicates in the first column the water pH value. As you know, 7 is neutral. Anything below is acidic, and anything above 7 is alkaline or basic. When we have water temperature indicated as 50 degrees Fahrenheit or warmer, we are given a contact time in minutes in the second column. In the third column, where the water temperature is 45 degrees, we are given the contact time accordingly. And finally, when we have a water temperature of 40 degrees Fahrenheit or colder, we have the given contact times in the very last column. For chlorine to be effective as a disinfectant, it must be in contact with the water for a minimum amount of time. Water temperature and pH both affect the amount of time chlorine needs to be completed in the disinfection from the system. From the table, it can be observed that chlorine takes longer at a cold water temperature. Look at the water pH of 6.0 and 50 degrees Fahrenheit or warmer. Disinfection is achieved after 3 minutes. Decreasing the temperature 10 degrees Fahrenheit, disinfection will take an additional 2 minutes or total of 5 minutes. Now observe the 50 degree Fahrenheit row and observe the effect of pH. At a pH of 6.0, which is slightly acidic, consider the disinfection would be achieved in 3 minutes. At a slightly alkaline value of 8.0, disinfection will take 16 minutes. Chlorine is more effective in acidic water than alkaline water. The water temperature and pH are important properties to know while disinfecting. Section 7.8.9, determining the volume of rainwater storage. We have an equation that's given to us. The solution gives us the rainwater storage volume in cubic meters. And the equation is D times N times D sub P divided by the quantity 1,000 plus floating. We will indicate where D equals rainwater demand in liter per capita per day, N is the population number, D sub P is the number of days which water will be stored. Consider 90 days for drinking, cooking, utensils, cleansing, bathing, and ablution purposes, 210 days for other purposes. On the next slide, we'll complete a design example to determine the rainwater storage volume of a small apartment complex building. Floating is a reserve capacity or factor of safety of water in excess of the design demand capacity. Floating volume could be utilized to handle excessively dry period or excessive use. A design example. Determine the rainwater storage volume for a 10-unit dormitory building. Assume the average number of residents per unit is 4. The rainwater will be used for drinking, cooking, and bathing purposes, and facilities are unrestricted. Let's take the first unknown in the previous formula, D, rainwater demand in liter per capita per day. What should we use as a value? Let's investigate another chapter of the BNBC and see if we can find any other information to help us solve this design example. We will look to Chapter 5. Water supply of the BNBC has several tables in Section 5.5.2 that provide design water consumption values based on socio-economic groups, type of habitants, population, and type of building. It is appropriate to use these values as a starting point in determining rainwater demand based on what is being supplied. Below is a portion of Table 8.5.1d, which contains the relevant information for our example. In our case, we're going to assume rainwater will supplement 25% of the design capacity, which will be 34 liters per capita per day. As we look at this particular table here, the class of occupancy that we have chosen is A, residential. The occupancy group, A4, and there is our dormitory in that line item. For full facilities, it's 135, and we will take 25% of that capacity as being 34. The next value is N, population number. To find this, we'll take 10 units and multiply that by 4 residents per unit. N equals 10 units times 4 residents per unit, equating to 40 residents. Next is D sub P, number of days for which water is stored based on use. In this example, we will use 90 days based upon our dormitory application. Last, for floating, the additional capacity, we will assume a volume of 1 cubic meter. Now let's put it all together. We will solve for the rainwater storage volume in cubic meters for our tank capacity. Below, we've plugged in the values in our equation. 34 liter per capita per day times 40 residents times 90 days dividing by 1,000 plus 1 cubic meter as the additional capacity for floating. That gives us a result of 124 cubic meter tank capacity for our dormitory design example. Sizing of rainwater downpiping, section 7.8.10. The size of vertical leaders or rainwater downpipe shall be based on the maximum projected roof area according to table 8.7.2. Minimum 2 drains and vertical leaders shall be provided for any independent roof surfaces. The size of semicircular gutters shall be based on maximum projected roof area according to table 8.7.3. As seen below, we have semicircular gutters and leaders taking the water into downpipes. Table 8.7.2, size of vertical leaders. The first column gives us the size of the leader in millimeters and ranges from 50 millimeters to 200 millimeters. The maximum projected roof area and flow are given in the second column in square meters, and the third column is the flow in liters per minute. Now there are notes to the table as indicated in the asterisk, single and double asterisk below. The notes are applicable when referenced. This table is based on rainfall of 25 millimeters per hour. The size of the leader will need to be adjusted to local conditions, as typical 25-year rainfall values vary from 65 to 100 millimeters in Bangladesh. The values can be obtained from the map located in Appendix R. Once the maximum projected roof area and/or flow are calculated, the value can be obtained directly from the table. Table 8.7.3, size of semicircular roof gutters. The first column gives us the diameter of gutter in millimeters. The range is from 75 millimeters all the way up to 250 millimeter gutter size. The maximum projected roof area for gutters of various slopes are indicated next. The second column gives us 5 millimeters per meter, as well as the area of roof in square meters and the flow in liters per minute. The next category is 10 millimeters per meter slope, 20 millimeters per meter slope, and last column indicates 40 millimeter per meter slope accordingly. This table is based upon a maximum rainfall of 25 millimeters per hour for a 1-hour duration. The figure for drainage area shall be subject to local conditions in accordance with Appendix U. This table could be utilized in multiple ways to determine the diameter. Once the projected roof area is known with a trail slope, the diameter of the gutter could be determined as shown. If a certain diameter were desired, for aesthetic reasons perhaps, it could be worked backwards to determine the slope of the gutter necessary for that roof area. This figure is taken from Appendix R of the BNBC and shows 1-hour rainfall values for a 25-year return period for various locations in Bangladesh. A 25-year storm has a 4% probability of happening in any given year. The red numbered lines on the map are the 25-year isohyets at 5 millimeter intervals, which designate the rainfall intensity. Rainfall for a particular location shall be obtained as follows. When the location lies within any region shown shaded on the map, the value marked for that region shall be taken. For a location lying on any isohyet in this map, the value of that isohyet shall be taken. For a location lying outside the positions of the two previous options, linear interpolation shall be made between the adjacent isohyets to obtain the required rainfall value. For example, a location that was exactly between 70 millimeters and 75 millimeter isohyet line, the value used would be 72.5 millimeters. Again, is the figure indicated 8.R.1. This is our 1-hour rainfall in millimeters map of Bangladesh, showing the rainfall intensities and isohyet lines in various areas of Bangladesh. A design example. Using tables 8.7.2 and table 8.7.3, determine the gutters and leader size for the building below if it is located in the city of Pabna. We have a building indicated in a roof plan. It is 25 meters by 40 meters. We have a roof sloping 5% downward towards an exterior mounted gutter with a leader at each end of the gutter. The first step is to calculate the project roof area. In this case, the roof area is calculated as follows. The roof area equals length times width. We have 25 meters times 40 meters equates to 1,000 square meters. If you recall, tables 8.7.2 and 8.7.3 are based on a rainfall of 25 millimeters. Let's look at a figure 8.R.1 a little closer on the next slide and find the design rainfall for Pabna. As we view the map and locate Pabna, indicated with the arrow, Pabna is very close to the 75 millimeter isohyet. So let's use that for the design. We will use a conservative value of 75 millimeters in our design. The design rainfall of 75 millimeters is exactly 3 times the 25 millimeter rainfall noted in design tables. To compensate for this difference, we will multiply the actual roof area by the factor of 3 to provide an equivalent volume of rainfall. The new roof area used for our design is going to be 3 times 1,000 square meters, which equals 3,000 square meters. Continuing our design example, to determine the size of the gutter, it should be noted that since the gutter is crowned in the middle, a given section will only serve half the design roof area. So 1,500 square meters is used to size the gutters. In reviewing the 5 millimeter per meter of slope column, the design roof area exceeds all the area values in that table. We need to now move to the 10 millimeter per meter area of the table. If we follow that column down to an area, we are looking for an area at least or greater than 1,500 square meters. Towards the bottom of the table, we find the value 1,850 square meters. We move to the left-hand side all the way over to the diameter of gutter, and we size the gutter at 250 millimeters. Last, we'll size the vertical leaders from the gutters. Remember, there are 2 leaders on the gutter. Follow the maximum project roof area column down to an area that exceeds our roof design area of 1,500 square meters. As indicated in the second column, we move down until we get a value that exceeds 1,500 square meters. As we can see, the value is 2,336 square meters. Moving to the left-hand side of the table to the first column, we size the leaders at 125 millimeters. That is, each leader on opposite sides of the gutter would need to be sized at a minimum of 125 millimeters. And this concludes our design. Section 7.9, Artificial Groundwater Recharge. Specifically, Section 7.9.1 gives us a general requirement. Stormwater runoff shall be used for augmentation of groundwater reservoir, where water depletion rate is more than 1 meter per year. The natural movement of surface water can be modified by constructing recharge structure, figure 8.7.1 previously shown, in order to obtain the following objectives. Enhancement of sustainable yield in areas where there is overdevelopment and depletion of the aquifers. Item B, conservation and storage of excess underground water in the aquifers. Item C, improvement of the quality of the existing groundwater through dilution. And finally, D, maintaining the natural balance of the groundwater and its usage, as the rainwater is a renewable supply source providing constant, dependable, and safe water supply. We need to be understanding of all of the items in this list and provide enhancement, sustainability of our underground aquifers accordingly. Designing recharge pit. Section 7.9.2. Volume of recharge pit shall be on the basis of maximum intensity of rainfall in a short period of at least 15 minutes. It's about 1/4 peak hourly rainfall. Capacity of recharge tank is given as a capacity equating to A times I sub S times F divided by P, where A is the catchment area, I sub S is the intensity of rainfall in 15 minutes, F is given as a runoff coefficient, and P is the porosity of the filter bed, equals 0.5. A large dry well can be constructed in accordance with the requirements for a seepage pit. You may want to see BNBC Chapter 6, Sanitary Drainage, Section 6.9.15. However, for small dry wells handling limited quantities of rainwater, the pit may consist of a 1 meter long by 0.545 meter diameter pipe filled with crushed bricks or stone. Section 7.10, Drainage and Sanitation Requirements. The object of stormwater drainage is to collect and carry the excess rainwater accumulating within the premises of the building for suitable disposal. In rainwater drainage system, there shall be a safeguard against fouling, deposition of solids, and clogging, and with adequate inspection chambers so arranged that the drains may be readily cleaned without the risk of health hazards. Specifically, in section 7.10.3, titled Imperviousness of the Surface, estimation of the quantity of stormwater shall be based on the following factors: the imperviousness of the surface, the ground slope and time of concentration, the intensity of the rainfall for a designed period, and the duration of the rainfall. Please be aware and keep in mind that excessive rainwater can cause flooding and other damage to buildings if not properly addressed. We'll cover each of the stormwater quantity factors on the slides that follow. Imperviousness of the surface. Section 7.10.3, the percentage of imperviousness of the drainage may be obtained from available data for a particular area. In the absence of such data, the following values may serve as a guide. As indicated, the type of area, commercial and industrial area, residential areas, high density, residential areas, low density, parks and undeveloped areas. The associated imperviousness factors associated with each one range from 70 to 90 regarding commercial and industrial areas, 60 to 75 for high density residential areas, 35 to 60 for low density residential areas, and 10 to 20 for parks in undeveloped areas. Commercial and industrial areas have a lot of impervious areas from buildings, equipment area, and parking areas. Most of the rainwater that falls on these areas will run off and cannot be evaporated or absorbed into the ground. These areas are usually high contributors to runoff, which is why higher imperviousness factors are necessary. The residential area imperviousness factor is directly related to the density of buildings and lots. Small lots with homes tightly constructed will yield more runoff than larger lots with more sparsely spaced buildings, and therefore have higher imperviousness factor. Look at the picture on the left, shows a high density residential versus the one adjacent to, which shows a low density residential. Parks and undeveloped areas provide the least amount of runoff. They remain mostly in their unaltered state with little or no impervious area which is why the imperviousness factor is so low. Time of concentration is indicated in section 7.10.4. Time of concentration to reach the farthest point of any drainage system or the outfall under consideration should be considered between 5 minutes to 30 minutes. The time of concentration is the time needed for water to flow from the most remote point in a watershed or a catchment area to the outlet. Small impervious lots would utilize a time of concentration at the lower end of the provided range, while larger sites, depending on imperviousness, would be at the higher end of the provided range. The time of concentration is needed for water to flow from the most remote point in a watershed or catchment area, of course, to the outlet that was described above. As indicated, for a given outlet of a ditch leaving a small building site, consider tracing a raindrop through a site from the most remote point. For example, a raindrop falls on a building's roof. It will travel down that roof to a gutter. It will then travel through the gutter, down the downspout or the downpipe. From there, through the downspout, it will terminate onto a sidewalk. It will then follow the slope of the sidewalk onto an adjacent parking lot. It will follow the slope of the parking lot to a ditch, where it will leave the building site. The duration of time that the raindrop took to travel that distance is the time of concentration. The intensity of the rainfall, section 7.10.5. Rainfall intensity data for the locality of the building shall be studied to arrive at the design parameters for rainwater harvesting in accordance with Appendix R. Appendix R was shown previously and provides the rainfall intensity for various areas of Bangladesh for a 1-hour 25-year storm. The rainfall intensity in millimeters per hour is the volume of rainfall to be applied over the design area. Rainwater disposal is specifically identified in section 7.10.6. It helps us understand that rainwater from roof or building premises shall not be discharged into septic tanks. This shall be drained into storm sewers or combined sewer systems where available, or into private disposal methods, water courses, or dry wells. For a sample dry well, see figures 8.6.18 and 8.6.19 below from Chapter 6, Sanitary Drainage. As seen, figure 8.6.18 on the left-hand side gives us a dry well orientation with respect to the roof drainage system down the leader into the storm drainage piping into the dry well. Figure 8.6.19 gives us installation details of a dry well. Specific to the dry well is the crushed stone or bricks around the outside. We have a precast concrete section or porous brick wall. We have drainage slots, and we have the rainwater from the building entering from the top as part of this particular dry well detail for installation. Rainwater should not discharge into a septic tank because the excessive flow would flood the septic tank and cause wastewater to leave the tank before it is adequately treated. That is why The septic tanks are prohibited. There are several options available to dispose of rainwater, and specifically indicated as such in this section. Disposal methods, watercourse, or dry wells, as we have just seen. 7.10.6.1 Individual rainwater traps shall be installed on the rainwater drain branch serving each leader, or single trap shall be installed in the main rainwater drain, that is the building storm drain, just before its connection with the combined building sewer, main drain, or public sewer. 7.10.6.2 indicates that no trap shall be required for rainwater drains, which will be used for rainwater collection and connection to a sewer draining rainwater exclusively. The first section, 6.1, indicated where we have a connection with a combined building sewer, main drain, or public sewer is where we need the trap. In this case, we need a water seal to prevent any harmful sewer gases from migrating back into the building. That is where we need a trap. A trap is necessary to prevent potential harmful sewer gases from working their way back through the rainwater drainage system into the building. Note that if the rainwater drain only serves rainwater, a trap is not necessary, as these sewer gases will not be present. So it's important for the designer and the installer and the inspector to understand where the rainwater system is being connected to accordingly. Specifics are given to us in section 7.10.6.3. Subsurface drainage piping for rainwater drainage shall not be less than 100 millimeters in diameter. The subsoil drainage system shall be protected by an accessibly located backwater valve in case the building is subject to backwater or flooding. 7.10.6.4 Rainwater pipes shall not be used as soil, waste, or vent pipes. A backwater valve can be an important part of a subsoil drainage system to prevent the building from flooding during a period of high flow. Building flooding is a nuisance and can cause unsanitary conditions under certain conditions. Off to the right-hand side, there are graphics of different types of backwater valves, as can be seen here. It is used as a protective measure to prevent any type of backflowing into that particular drainage system. Section 7.11, Materials and Appliances. The piping, fixtures, and equipment to be used for rainwater harvesting and drainage system shall be in accordance with section 6.7 in chapter 6. The following slides will provide the code user with acceptable piping and fitting materials for rainwater harvesting and drainage systems as referenced in section 6.7 for building drainage and vent piping. Table 8.6.3b, titled Recommended Standards for Building Drainage and Vent Pipe. The materials are indicated on the left side of the table. Standards are indicated on the right side of the table. We have ABS plastic pipe and the associated standards. Aluminum tubing is a material that can be utilized for building drainage and vent pipe, as well as brass pipe, cast iron pipe, copper or copper alloy tubing. We have galvanized steel pipe that is permitted, and polyvinyl chloride plastic pipe, better known as PVC. As an example, Schedule 40 ABS plastic drain, waste, and vent pipe is and properly addressed as complying with the standard ASTM D2661 for that particular material. Again, Schedule 40 ABS plastic drain waste and vent pipe. Additionally, Schedule 40 PVC plastic drain waste and vent pipe must comply with the standard ASTM D2665. Table 8.6.3E, titled Recommended Standards for Joints Between Different Pipes and Fittings, allows us to locate materials and standards for different types of pipes and fittings accordingly. As an example, all of the materials are indicated in the left-hand portion of the table and the standards in the right-hand portion of the table. Again, we have an example of an ABS type of material. In this case, it's a plastic pipe fitting called a coupling. We also have PVC plastic pipe fittings and the associated standards. As indicated below, we have what's called a sanitary tee, and that is PVC plastic pipe material. So again, the designer can reference this particular table and specify pipe fittings and the associated standards for those particular fittings. Section 7.14, Hangers and Support. The piping fixtures and equipment used for rainwater harvesting and drainage systems shall be provided with sufficient hangers and support in accordance with Section 5.17 in Chapter 5, Part 8. The following slides will provide the code user with acceptable piping, hangers, and support as referenced in Section 5.17 in Chapter 5, Part 8. Referencing Section 5.17 in Chapter 5 for piping hangers and support requirements, Section 5.17.1, Galvanic Action. We need to make sure that we do not have dissimilar metals in contact with one another. If we do, that may provide and even promote galvanic action. Section 5.17.2, Hanger Spacing. Vertical and horizontal piping shall be supported in accordance with Table 8.5.14. As an example, the picture below indicates piping being supported from the building's structure by means of a threaded rod and a hanger that goes around the pipe that we know as a teardrop hanger. Table 8.5.14, Hanger Spacing, gives us the piping material in the first column, the maximum horizontal spacing in meters in the second column, and the maximum vertical spacing in meters in the last column. According to the drawing below, the maximum horizontal spacing. If we have galvanized steel pipe to be supported, we need to enter the table's piping material. Galvanized steel pipe, in the application as indicated in the drawing, we want to know the maximum horizontal spacing for galvanized steel pipe. And by applying the table, we can see that the maximum horizontal spacing for this particular material, galvanized steel pipe, is 3.5 meters. For the PVC pipe that is indicated in the drawing, the maximum horizontal spacing between hangers for PVC pipe is 1 meter. Special care for rat proofing is addressed here. specifically requiring that we seal pipes and openings around equipment for the prevention of entrance of rats into the building. Rodents can enter a building through annular spaces around piping that penetrates a wall, ceiling, or floor. These spaces must be blocked using caulking or gasketing. Methods and materials must provide an effective barrier that would restrict the passage, again, of rats into buildings. The graphic shown to the right of the slide indicates pipe openings into the building are protected to prevent the entrance of rats into the building. Section 7.17, Gradient of Pipes. Lesser slope of rainwater drainage pipe shall be provided. The computed velocity in stormwater drains shall not be less than 0.6 meter per second. The maximum recommended velocity shall be 2.5 meters per second. For drain pipes to be used for recharging, the flow velocity should be 0.6 meter per second. The minimum velocity is required to keep sediment in the rainwater suspended. At lower velocities, sediment could settle out and be deposited in the pipe. Over time, this sediment can build up, obstruct the flow, and eventually clog the pipe completely. High velocities are not recommended as they can cause erosion to the interior wall of the pipe and of the soil at the pipe outlet. Section 7.21. Sizing and finding the number of rainwater drainage piping. Specifically, 7.21.1 indicates the size and the number of vertical liters shall be based on the maximum projected catchment area according to Table 8.7.2. Minimum 2 numbers of roof drains and vertical liters shall be provided for any independent roof surface. 7.21.2 provides the size of building storm drain, storm sewer, or any of their horizontal branches shall be based on the maximum catchment area included. Projected roof or paved are to be drained in accordance with Table 8.7.4. The size of semicircular gutter shall be based on the maximum projected roof area according to Table 8.7.3. Tables 8.7.2 and 8.7.3 were covered in previous slides and in a design example. As you remember, Table 8.7.4 works very similar to those tables. However, this is for horizontal branches or main of a storm sewer. We'll cover Table 8.7.4 on the next slide. Table 8.7.4, titled Size of Horizontal Building Storm Drains and Building Storm Sewer. This table is used for the horizontal connections. The first column is given our diameter of drain in millimeters. It ranges from 75 millimeters all the way up to 375 millimeters. The maximum catchment area and flow for various slopes are given in the second, third, and fourth columns. The second column indicates 10 millimeters per meter, gives us the equivalent area of roof and liters per minute flow rate. 20 millimeters per meter in the third column gives us the area and flow. And finally, in the very last column, 40 millimeter per meter slope, again gives us the area and flow rate accordingly. Again, remember that this table is based upon a maximum rainfall of 25 millimeters per hour for a 1 hour duration. As with the previous design tables covered, this table also is based on a 25 millimeter per hour rain and needs to be adjusted based on local conditions. To determine the diameter of a horizontal building storm drain, the catchment area needs to be calculated. This would include all areas draining into the said storm drainage, and could include areas such as the building roof surrounding sidewalk and parking lot. Once the area is determined, the drain slopes can be evaluated to determine the final diameter of drain. A drain with a steeper slope will have a higher flow capacity and therefore can yield the use of a smaller pipe. Section 7.22, Inspection, Testing, and Completion Certificate. The Inspection, Testing, and Completion Certificate of rainwater harvesting and drainage system or part of existing system shall be in accordance with Section 6.15, Chapter 6, Part 8. The following slides will provide the code user with information contained in Section 6.15 of Chapter 6, Part 8. Chapter 6, Section 6.15 indicates the new drainage and sanitation system or part of the existing system shall not be covered or enclosed or put into operation until it has been inspected, tested, and approved by the authority. The authority may examine the appliances and fittings before their installation or during the progress of work. An installation of plumbing work, whether new or existing, which is found to be defective or unsafe, shall not be allowed to continue in use unless corrections have been made to comply with the code requirements. Now, this also is in effect for rainwater harvesting and storage and drainage systems. Section 6.15.2, titled Testing. The piping of drainage and venting system shall be tested first with water. The final test of completed drainage and venting system may be done by smoke test. The water and smoke test shall be performed as described below. Item A, water test. The water test shall be applied to the drainage and venting system either for the whole system or part thereof. For the entire system, all openings in the piping except the highest opening shall be closed, and the system shall be filled with water to the point of overflow. For the system to be tested in sections, each opening shall be tightly plugged except the highest opening of the section under test, and each section shall be filled with water, but no section shall be tested with less than 3 meter head of water. In testing successive sections, at least the upper 3 meters of the next preceding section shall be tested so that no joint or pipe in the building shall have been submitted to a test of less than 3 meters a head of water. The water shall be kept in a system or in the portion of the system under test for at least 15 minutes before the inspection starts. The system or part of the system under test shall be watertight at all points. Item B, smoke test. The final test for gas and water tightness of the completed drainage and venting system may be performed by smoke test. The test is performed by filling all traps with water, then introducing smoke into the system by one or more smoke machines. When the smoke appears at the stack openings on the roof, they shall be closed, and a pressure equivalent to 25 millimeter head of water shall be built and maintained for 15 minutes before inspection starts. Section 6.15.3 is the completion certificate. After the installation of drainage and sanitation system, the licensed plumber shall give a completion certificate to the authority in a prescribed form, indicated in Appendix T, for testing and inspection. After testing, the authority will give the final approval as presented in completion certificate form in the Appendix T to use the system. As we see an example in Appendix T, the completion certificate. It indicates the reference number of the authority's permit, the date, and the language stating this is to certify that I or we have completed the drainage and sanitation system for the building and the premises at a certain location. Detailed description of the work is required, and indicating this may be inspected, tested, and approved, and the signature of the plumber with the name and address. Down at the bottom of the form or the certificate, the authority certificate, it indicates this is to certify that the above drainage and sanitation system has been completed in accordance with the provisions of the Bangladesh National Building Code. The drainage connection to the main sewer, if any, may now be made. And last is the signature of the building official or his authorized deputy. This also is the completion certificate as recommended for rainwater management systems in Chapter 7. Section 7.23, Guide to Maintenance. The maintenance of rainwater harvesting and drainage systems shall be in accordance with Section 6.16 of Chapter 6, Part 8. The following slides will provide the code user with information contained in Section 6.16, Chapter 6, Part 8. In order to keep the rainwater harvesting and drainage system in peak operating condition and clean, maintenance is important. That's why we are referred to this section, Section 6.16 of Chapter 6, for these requirements. In Section 6.16.1, it indicates the drainage and sanitation system shall be maintained in a sanitary and safe operating condition by the owner or his designated agent. All device or safeguards required by the code shall be maintained in working order. This particular section indicates that the owner or the designated agent of the owner is responsible for the maintenance of these systems. 6.16.2, the following operations shall be carried out during periodical cleaning of a drainage and sanitation system. These items are specific not only for sanitary drainage, but also rainwater harvesting and drainage systems. A, the covers of inspection chambers and manholes shall be removed, and the side benching and channels shall be scrubbed. B, all lengths of main and branch drains shall be rotted by means of drain rods and a suitable rubber or leather plunger. After rotting, the drains shall be thoroughly flushed with clean water. Item C, the ladders, rings, and deep manholes and the manhole covers shall be painted. All surface drains shall be cleaned. All subsoil drains shall be examined for obstruction at the open joints. Any refuse chute system shall be cleaned. These particular sections give the guide to maintenance, again, for rain harvesting and drainage systems, as indicated in Chapter 7, Section 7.23. Chapter 7, Miscellaneous. In conclusion, it's worth noting for the code user that several sections of this chapter reference various sections of Chapter 5, Water Supply, and Chapter 6, Sanitary Drainage for specific requirements, which are outside the scope of this presentation. These sections include Section 7.11, Materials and Appliances, that reference Section 6.7. In Chapter 6, we saw some of the materials that were allowable utilizing Chapter 6, Section 6.7 specifically. In Section 7.12, Construction of Rainwater Storage Tank, referencing Section 5.9 in Chapter 5, needs to be noted. Section 7.13, Installation and construction of rainwater harvesting and drainage systems, references Chapter 6, specifically Sections 6.9.9 and 6.10.2. Hangers and supports in Section 7.14 reference Chapter 5, specifically Section 5.17 in Chapter 5. Pipe joints in Section 7.15 again reference Chapter 5 in Section 5.17. So as can be seen here, there are several references to different chapters and sections that the code user, the designer, the installer, the inspector, and the code official must reference for rainwater management systems that include harvesting and storage of rainwater systems. Continuing our list, in Section 7.16, Protection Against Rodents, Section 6.9.8 was referenced in Chapter 6 for rodent protection. Section 7.18, Inspection Chambers and Manholes. We have a reference to Chapter 6, specifically Section 6.9.7.4. Bedding and backfill in Section 7.19 was referencing Chapter 6 in Section 6.9.9. Section 7.22, Inspection, Testing, and Completion Certificate, references Section 6.15 in Chapter 6. And finally, Section 7.23, Guide to Maintenance, gives a reference to Section 6.16 in Chapter 6. This is the end of the presentation. Thank you for your participation.